So today I'm going to talk a little bit about what is functionality, the types of functionality that are important, and the specifically focusing on physical characterization, physical functionality, the tests that are available to analyze these functionalities, tests that can be done in-house or at Camden BRI, and how those tests and how understanding functionality can be useful for your process for improving product quality, consistency on plant, reducing waste, these sorts of things. So what is meant by functionality? Simply, functionality is the reason why you are using that ingredient. Why are you putting in that ingredient in the first place? There can be lots of reasons why you would put an ingredient into a product: flavor, nutrition, enrichment. However, quite often it's done for a physical purpose, a texture, to improve texture or structure, or as well as the nutrition enrichment. And it's the texture and structure that we'd be focusing on for the egg. So that is, if you take a look at the image on the right hand side, that's some sort of pastry which has a very interesting structure. Are eggs playing a role in that? Is it the wheat dough? Is there a batter, some lamination going on there? So what ingredients are contributing to the structure of the bottom bit? You've also got a curd, which is a type of an emulsion. So eggs are being used to combine fat and aqueous phases to make emulsions. So that may be another function of using egg to make emulsions. Or the top is a meringue layer, so it's a foam. So the egg whites are being specifically used to create a aerated structure, and it's these structures and textures, especially in baked products, but in other things as well, mayonnaises. It's this texture and structure which provides the mouthfeel, the richness. And the delicateness of certain products which consumers find so appealing, fluffiness of cakes. Eggs are used to make these structures. Egg is one of these super ingredients that is highly functional. And when I say highly functional, I mean it's providing lots of functions. It's in there for lots of reasons. It's in there to stabilize air bubbles, especially in cakes. I'm specifically talking about here. You need air within the batter stage to be stable, because those air bubbles then expand during baking to give you that structure. Emulsification is really important as well. And eggs are very good emulsifiers. So that may be one reason why you're using the eggs, especially if you're making sauces or mayonnaises, salad dressings, for example. And another one of the key functionalities is gelling. So we all know when you cook an egg, it turns from a liquid into a solid. And this is a really useful property for baking when we are making these interesting structures that are for cakes and other things like that, even things like meringues. Once you have created the structure, you want to set that structure and you want it to stay like that during its life. So these are the key things we'll be talking about today. So the driving factors. So these may be some of the reasons why you're here today. We are finding more and more at Camden that people are coming to us and are worried about the variability of their egg materials. They may be bakers, they may be making other products using egg, and are finding that the variability of batches is inconsistent and the quality is often not what it should be. Now, sometimes this can be egg can be identified as the ingredient. Sometimes you may not know what is causing these inconsistencies, but that still is important to understand how do your ingredients vary in the properties that are most important, i.e. their functions. There's a lot of focus on egg in the media and in the industry at the moment. It's rising costs are causing people to look for new suppliers, look at new materials. And eggs are also, one egg is not the same as another egg. One egg material you buy from one supplier is not the same as another egg material. Eggs can vary, egg materials can vary in their functionality, the effect of processing. So quite often where eggs, liquid whole egg has to be pasteurized, has to go through a heating process. That heating process can decrease some of the functionality. Sometimes eggs are turned into egg powders. How these are spray dried, the temperatures that these are spray dried at can affect the amount of denaturation and therefore the amount of functionality of these products. Also, the conditions of the chickens that are producing the eggs is important. The age of the chicken, the age of the eggs, the rearing conditions, so its feed and other conditions are really important in in producing consistent eggs. Different feed may give different levels or ratios of protein to fat, etc. There's also a concern at the moment of bird flu, so lots of chickens are being kept indoors rather than outdoors. What effect is that having on the materials? Now, we don't necessarily have the answers to those questions, but what I want to try and promote today is, as manufacturers, you should be able to understand what the materials you are buying can do for your process. What parameters about the materials are important for your quality and consistency. These are quite often parameters that are not given on the specification. Now, some things, some egg materials do give some parameters, such as high gel egg white powder or high whip egg white powder. And that can be useful to those manufacturers, but one supplier of high gel egg powder, if you want to compare that to another supplier of high gel, how are they measuring it? Quite often these the methodologies are not consistent between suppliers, and also there's no the methods are the results, sorry, are method specific. So how you measure the foaming ability of an egg matters on what the results are. So you cannot necessarily compare two results from two different suppliers. And it's that key thing that this information is currently not available on specifications. An example of what I'm trying to describe here is if you think about the wheat industry. Now, people who maybe are baking manufacturers will understand that when buying wheat flour, which has a very specific plant protein, gluten forming proteins, which has a very specific functionality of elasticity, these specifications currently come with very specific tests. There's tests for the enzymes, there's tests for water absorption and dough development, there's tests of extensibility. Now, these are all specific tests for a specific ingredient. Effectively, what I'm proposing is that there are similar but more specific tests to egg which are available, which can provide useful information, just like the wheat flour tests provide useful information to those buying wheat flour. Now, this is just a little bit of a diagram to show you what I'm talking about here. So we want to analyze the functional properties of our ingredients. We want to know more information about our ingredients. In particular, we're talking about egg in this presentation. It's then really important to relate these functional properties to your process and to your product quality. One of the key messages to take away from these presentations is it's one thing to understand the functional properties of an ingredient, and then there's a secondary part to that of how do these functional properties affect the process and the product quality. Once you know which functional properties are important and which tests are important, you can start being more savvy about selecting tests that you can add on to a specification to allow you more information and more control over your ingredients. So you want to identify which are the best properties. You are then able to predict the quality of your final product. You're able to monitor the variation between batches of ingredients. And I've got an example later on today of some of the variation that can be found between different batches of ingredients. You may be looking at finding different suppliers of potentially cheaper ingredients, but when doing so, you need to be sure that you're not going to change the process or reduce the final product quality. So you need to understand what parameters, what functional properties of that ingredient are important to your product. And the key message is that this is very specific to your process and your product. A single, so for example, the gelling properties of an egg or an egg material will be very important for cake manufacturing, but may not be so important for mayonnaise manufacturing. And specifically, the type of cake, the oven, the bake profile, if eggs are setting at different temperatures, then this can have an effect on your final product quality. You will want to keep the setting temperatures of your egg materials consistent, or at least know when a batch of materials has a different setting temperature. And of course, why is this useful? It will save money in the long run. It will save you throwing lots of product away because it's not to the standard that it should be. And hopefully, when you have a good idea about your ingredients, what they are there for, and how to monitor the ingredient quality, you can keep that going and keep a better eye on them. So when changes do occur, you have more oversight and transparency of your ingredients. So I'm going to go into a little bit about different types of functionality for egg. So egg, as most people know, is a very good foaming agent. That is whole egg as well as egg white. Everyone knows egg whites are good foaming agents, but egg as a whole egg can make a very stable foam as well. It's the proteins in the eggs, in particular the albumins, that unravel and denature very temporarily when whipping the egg, and are able to stabilize the air bubbles and stabilize the foam structure. Now, if aeration of a product is important, then are you monitoring the aeration properties of the egg? Maybe, maybe not. And it may not be obvious. If you're making meringues, then you probably are. But something like cake, the aeration properties of cake batter is really important. So are you aware of how the aeration properties of egg impacts the quality of your cake? Maybe not. So there's different ways that you can measure the foam expansion, the foam properties of your egg. One simple way is using a benchtop whisk, a simple home style Whisk, KitchenAid, Kenwood, other brands are available. And you whisk it for a consistent amount of time. You can then take the egg and measure the overrun. So if you have a pourable foam, you may be able to pour it into a measuring cylinder and measure the foam. If you have a stiff foam like you do there, you may have to do a calculation by filling a known volume and measuring the weight, and that way you can measure what's called the overrun. It's a way of extrapolating the foam expansion. If you know the weight of the starting egg and you know the weight of the final whipped egg of a known volume, you can calculate overrun or foam expansion. Now, one thing we have had very recently approved and has not yet arrived, but we have had approval for a new piece of equipment called a dynamic foam analyzer, which does very controlled foam whipping analysis. So we're hoping to roll that out in the next few weeks and get that being used for egg functionality and plant protein functionality as well. Now, the fundamental measurements of aeration are important and can be analysed as well. So aeration works on reducing the surface tension of water. So it's very hard to whip water, but when you add surface active molecules like albumins, they are then you can reduce the surface tension and create surfaces, i.e. bubbles. We have different ways of analysing surface tension here, but the main one we use, which is very accurate, is what's called drop shape analysis. And there's a little image in the bottom left-hand corner. And you basically make a pendant drop of the egg solution, the egg liquid, and the shape of the drop can be analysed to give the surface tension. That surface tension can relate directly to its foaming and aeration abilities. The other fundamental property that's important for aeration is viscosity. Viscosity is what we call the kinetic barrier for foam collapse. So if you have a thick, viscous egg, or what we call the continuous phase, the bit that is holding the foam together, the more viscous that is, the slower the liquid will drain and the slower the foam will collapse. So understanding the liquid's viscosity can give you an indication of foam stability. Moving on to emulsification. So obviously emulsions are a mixture of fat or oil droplets dispersed within an aqueous phase. You can also have an aqueous phase dispersed within an oil phase. Most food emulsions are oil in water. Some exceptions include butter, for example. But quite often it's the oil in water ones that are of most interest, the milks, creams, mayonnaises, and it's the proteins and also other surface active molecules, phospholipids such as lecithin, which are also surface active, can stabilize oil droplets. Now you might be thinking, how can you analyze the emulsion capabilities of eggs? And one thing we do here at Camden BRI is we make model emulsions. So we create an emulsion with a certain aqueous phase, a certain amount of usually rapeseed oil or sunflower oil, and we create model emulsions at a certain ratio, and we deliberately try and induce a certain amount of instability. We don't want to make thick mayonnaises. What we want to do is create a certain amount of instability so they become unstable. But once they become unstable, we can monitor the rate at which they become unstable and directly compare the stability capabilities of these different materials. We can also analyze the physical properties of the emulsions themselves. We can measure the particle size distribution. Particle size distribution is a good indication of emulsion quality. If you have a range of particle sizes of oil droplets, then your emulsion is likely to be more unstable. If you have a very consistent size of oil droplets, then you're more likely to have a very stable emulsion. The size of those is really key as well. So smaller droplets can be more stable. We use a high shear mixer for that. But there are other ways that we can look at this more fundamentally. Now, I mentioned the drop shape analyzer measuring the pendant of the drop. We can also measure interfacial tension. So what is the surface tension or interface tension between air and oil, or between the aqueous phase, i.e. egg, and oil? How does that interaction, what does that interaction look like? Is the surface tension higher or lower than, say, another material? And I've got some examples coming up. And finally, gelling. This is often one of the tricky ones for people to try and when replacing egg, finding something that sets solid when heated. It's due to the denaturation, so the unraveling of the proteins at a certain temperature, around 50 to 70 degrees. And then the key part is the coagulation. So once these proteins unravel, denature, they expose the interior functional groups, which can then make links to the inside of other proteins and create a network. And that's what the gelling is. Lots of proteins denature, but not all proteins coagulate, and that's where eggs are useful. There's different types of analysis that we can do on egg gelling to understand their properties. Differential scanning calorimetry, or DSC, is a useful one. It's a thermal technique used to analyze the temperature ranges of thermal transitions, for example, protein denaturation or protein coagulation. It works by measuring the change in enthalpy at certain temperatures. So during an exothermic or an endothermic process, such as coagulation, energy is taken in and the thermal equipment can detect that. We can also measure so not just the range of temperatures that is important, but how energetic was that transition. We can measure that as well. RVA analysis, this is rapid visco analysis, typically used for flour and starches, but we have been using it at Camden to analyze protein and egg materials as well. It's effectively a viscosity measurement during heating. So we can analyze the changes in viscosity while we cook something, while we heat something up. And there's an example coming up for egg in the next slide or two. It has its drawbacks though. Obviously, because it is a viscosity measurement, viscosity can only be measured on liquids. You cannot measure the viscosity of a solid. So we either have to use low concentrations. Oh no, we have to use low concentrations or only be able to analyze the part of the RVA trace while it is liquid. As soon as it sets, we can no longer take a viscosity measurement. However, we do have what's called a rheometer here at Camden, and that can do oscillatory measurements. So instead of stirring like the RVA does, which is where when it becomes a solid becomes a problem, we can do oscillatory measurements. So it just goes back and forth slightly without breaking the structure. We're able to then measure how what we call the viscoelastic properties. So how liquid is it? How solid is it? When does it start to increase? What temperature does it start to increase? What rate does it start to increase? And we can then look at this and see how that changes as it cools as well. and one other measurement of gel strength for of gelling for egg. And now this is one that I find very common amongst manufacturers. However, my experience has been fairly limited with it. We have found it not as useful as some of the other techniques. What this one is where you take, and it is usually based off a similar test for gelatin called the gelatin bloom test, where effectively you take a pot, you cook it in you put some liquid egg in there, you cook it in a water bath at 90 degrees, I think. It sets, you then let it cool. How long you let it cool? Usually overnight. At what temperature do you cool it? It's usually around 10 degrees, I think. And then you use a texture analyzer to measure the force required to compress and penetrate into the gel. There's lots of tricky things with this method that I alluded to. How long do you cook it for? How long do you cool it for? What temperature control do you have as it's cooling? There's lots of things that can make this very difficult in practicality. But it can be useful, but sometimes some of the more involved measurements can give better indication of how it relates to your process. Because very often your products you're not cooking them, cooling them overnight and then measuring them. It's the changes that are happening during the process which give rise to the good performance or bad performance. Now, this is an example actually from one of our clients who's given permission for me to discuss this today. This is some rapid Visco analysis, RVA analysis of around 13 different egg powders. These are all egg powders that were being used in this manufacturer's process. They were unaware of any differences between these egg powders. However, they were aware of lots of variation in quality. They were unsure about what was causing the variation in quality, but they had narrowed it down after going back through batch codes, etc., that they thought it was to do with the egg. Now, those of you who have not seen an RVA trace before, you have viscosity along the y-axis and time across the x-axis. The temperature profile that we specifically used for this one is shown in red, and the y-axis on the right-hand side. But what we're looking at is, as we heat it up, how does the viscosity change? Now, these egg powders were all put in exactly the same solids to water ratio, sample to water ratio, and this is the variation that we got. So we got some increasing to 800 centipoise, some barely increasing at all. Now, initially we looked at the final viscosity and was trying to correlate this with good and bad samples, and although it was interesting to see that there was a variance, there was no obvious correlation between final product quality. However, what we then noticed was there is a discrepancy between when these samples are setting. So at what point do they start increasing in viscosity? What temperature do they increase in viscosity? If I zoom in on this, you can see there is such a range between these egg powders in when they begin to set and how much they begin to set. And it was looking at this setting point which gave a much better correlation between the batches that were causing problems and the batches that were not causing problems. If you have an egg powder that sets too early in something like a cake baking, then you are not allowing time for the cake to expand and you don't get the structure that you want. If you have an egg that sets too late, what you get is an expansion and then a decrease as the bubbles rupture, and then it sets and you don't get the final product quality that you require. And that's a key point that I'm trying to make that this is very product specific. There is not one test that is going to be perfect for every single application. I'm aware I'm running quite late, so I'm going to go through this a little bit quick so we've got time for questions. So here's another example that we've done in-house here at Camden BRI. We've done some surface tension measurements in the top left between two samples of egg powder, and we have found a difference in these. One had a much lower surface tension than the other when doing it on drop shape analysis. We also found that when mixed with water, these egg powders had different viscosities. When we did the temperature sweep using the oscillatory rheometer measurement, we found maybe quite similar. However, there was definitely a difference between the two. The purple one, sample 1, set earlier and stronger. The straight line at the top going backwards, is it cooling? And it seemed to cool to a very similar. But the results that we saw from this, when we then used those same two egg powders to make cakes, is that sample 2 cake, so the one with the lower surface tension, gave a bigger volume cake and a softer texture. So volume and texture are often related, but what we're seeing with two of the exactly the same recipes, only difference is the egg powder. It was the surface tension that gave a good indication of the quality of the cake. Now, this could be stabilization of air during the mixing process. However, on review of the batter densities, there was a difference, but it was small. So it could be the stabilization of the air bubbles during the baking as the bubbles are expanding. That could be what's key. So just to reiterate these points, it is specifically for your product is useful to understand what functionality properties are important, and not just important for your final product, but important for your intermediate products, such as batters. So all of the analysis that I've shown you, the gelling, emulsification, and aeration, is important to be able to understand the physical properties of your batters and be able to monitor those. So you may monitor batter viscosity, you may be able to monitor batter density, batter rheology, so we can do similar measurements to those similar measurements to the egg oscillatory measurements on the rheometer. We can do that with cake batter. One of the barriers that are there for cake batter is it's very difficult to analyze the rheological properties of cake as it expands. However, we can take the air out, and we can do the rheological properties of once we've used a vacuum to remove all the air bubbles, so there is no expansion. So yeah, one other key thing that we can look at is the cake during baking. So this is again an example for cake. We have an oven with a camera set up to it, which can look through and measure the height to the top of the cake and measure the rate of expansion of the cake. We can relate this to the cake rheological properties as well. So this is a fairly new technique that we've used a few times here at Camden BRI, and looking to find some partners who want to have a go at this and see how the rheological properties of their ingredients affect the rheological properties of their intermediate products such as batters, and therefore impact the baking properties, the expansion and collapse of the foam to sponge formation of the cake. How do different ingredients, different temperature profiles, there's lots of things we could apply to these sorts of techniques to do some really cool science. Another thing I can quickly show you here is some work we've done at Camden BRI, where we've hired a medical MRI scanner, which was quite strange to see in the car park, and used a custom-made oven that could go inside the big tube, and we could measure the density of the cake and look at how the structure changes over time. So I thought that was quite cool to include there. But what it does is it shows you the importance of the physical properties of the system during baking. How does the batter rheology affect how much it can expand? And that's one of the key messages to take home. Okay, now I can't. There we go. I just wanted to put this slide up at the end just to show you how I think understanding your ingredients better can improve your products and your process, reduce waste. So yeah, one final slide to touch on. You may be able to identify products that are good, and you may then want to know more. Why are these egg materials better than other egg materials? It may be the composition or the biochemistry of those egg materials. We may want to look at the fat content, the protein content, the fatty acids, the protein sizes or the protein size distribution, the amino acid profile, what amino acids are there. This can affect functionality because the functional, when coagulating, there's a certain few amino acids that link together to create the coagulation gel network. So I've explained quite a lot about the physical properties analysis that we can do at Camden, but remember, Camden is a massive organization with a lot of capabilities. And if you're interested in doing more analysis about why there are differences, then we're certainly interested to help with that. As an example of SDS page, which is one technique that we can do here to analyze the size of proteins of materials. So very quickly, egg materials can vary in their functionality greatly, as shown in some of those examples. And quite often, this variation is due to the functional properties, and the variation in functional properties is not shown on specifications, or if it is, may be very specific to that supplier and cannot be compared to another supplier's identification of its functional properties. How you relate that to performance is specific to your product. So if you have different lines making different products, the egg may be being used in different ways, and different properties may be more or less important. Yeah, we want to help you make better choices about buying ingredients, maintaining consistency and quality, and overall win-win for everyone. Reducing waste and saving money is the one of the key objectives for many companies this year. Now that took longer than I thought it would, so we only have 12 minutes to answer some questions.